All right, welcome all. So I spent a lot of time thinking about what we should be doing for the remainder of the course. Well, I've been thinking about it a lot even before the semester started. Luckily, I've come mostly to the same conclusions as a few months ago. So in this, what made me pause is your next exercise, where you are going to read a few of the papers that describe the benchmark winning pipelines for really very advanced computer vision tasks. And I think after following a few lectures that we've had so far, you will be able to understand most of those papers. And I find that so irritating. So, it either says as a field, we're doing something really right, or we're doing something really wrong. I'm honestly not sure which. The fact is, though, that what exactly is benchmark winning, how precisely the pipelines look, that changes from year to year. So I'm not very interested in teaching ephemeral knowledge, things with a very short best before date. Well, I had a few more guiding thoughts, namely, if you want to build something, you can only construct using the bricks that you have, or using the tools that you know. And those benchmark winning papers, they are essentially highly engineered convolutional neural networks with not very many, well, there is a lot of engineering, but somehow they're pretty pure CNNs. So likening this to Lego, I like to think of them as your nice square bricks. You can build amazing things from just nice square bricks. So if you go to Legoland or elsewhere, you will see fantastic constructions. But for example, they will not be very mobile. So sometimes bricks are wonderful, but perhaps you may need a hinge. Well, I want you to know that hinges exist in Lego, and there are things other than CNN in computer vision. Also, later in life, when you learn things, you will always have or probably will have a lot of short deadlines. So if you happen to work in computer vision in a company, often the task will be to solve problems immediately. Yesterday, please. And that means you will, also if you don't work in computer vision. So the time that you study now is the time to learn the hard things. The easy things you can pick up later. So I want to talk about a few things. Are they harder than CNNs? I don't know, but they are conceptually a bit different. Now, when deciding what to talk about beyond CNNs, this is of course a gamble. So will CNNs alone be able to do everything we want to do one day? Perhaps yes, perhaps no. I tend to think no. And then the obvious question is, well, if it's not going to be CNNs, what will it be, or what will we want to use? And there the answer is I also don't know. But well, I have some thoughts nonetheless. So one thought is that in computer vision and in video, we're dealing with millions and billions of pixels. So of necessity, we will be restricted to working with very efficient algorithms. And it turns out that in computer science, there's only a short list of fundamental problems that can be solved efficiently at all. More comments about that on the next page. Now, when I say they can be solved, I mean they can be solved exactly. Now, how important is it to solve problems exactly? I'm not so sure. Probably in computer vision, not. The important thing is to draw the correct conclusions. It's fine if in between you did not solve a problem in a globally optimal fashion. Still, these short list of problems that can be solved efficiently, they are usually part of heuristic algorithms that solve even harder problems that cannot be solved efficiently, of which there are many more. So I think it makes sense to be acquainted with these problems that can be solved efficiently and be acquainted with, so to know that first of all, and secondly, to understand a little bit how these problems are solved, being able to recognize them. That hopefully, will give you new bricks or new tools to do more interesting things or solve harder problems than are possible so far, than are possible today. By, of course, standing on the shoulders of giants, in this case, computer science giants. So one focus will be on problems that can be solved optimally, efficiently. The other focus that I've decided to use here is to have algorithms that are, most of them at least, applicable to graphs. Why? Because I think graphs are pretty universal, or afford a pretty universal formulation for many kinds of problems, and I think they could matter when you go to higher level tasks, such as understanding or describing what's going on in a scene, describing a set of actions, describing the interactions of agents, or describing knowledge. And there's a thing called knowledge graph. And I don't know if graphs will be used for that 20, 30 years down the road, but I could very well imagine that they will be. Good. So these are my preliminary conclusions as to what could matter to you most. And here I have a big overview of problems so some broad classes of problems that can be solved efficiently. There are path compression problems with a practically linear complexity, which are used in the disjoint set or union find data structure. So the complexity here is n, where n is the number of observations. The same complexity applies to estimating lower envelopes, at least if one of the two functions is convex. And this has applications in computer vision, for example, in certain morphological techniques that we'll talk about, 1D distance transform, and so on. Then there's the class of divide and conquer algorithms, which are famous techniques used in sorting. This gives you the fast Fourier transform. It can also give you lower envelope of more general classes of functions. I will not talk about the divide and conquer class so much. Why? Because, well, I think sorting is a primitive. You will probably not implement that yourself in life. And everybody understands a sorting, or everybody recognizes a sorting task when they have one. But some of these other problems are harder to recognize, and I think it makes sense to talk about them more. So dynamic programming is of huge importance, and in there's a class of problems, so-called finding shortest paths, which we'll talk about today, but also finding widest paths or number of paths. message passing on trees, backpropagation, all of these are examples of that can be solved efficiently using dynamic programming. All of these have already had important uses in computer vision before CNNs. Some of them are still important in CNNs, like backpropagation. I think some of these may again become important after CNNs or in conjunction with CNNs. And then there is the class of flow and cut problems, such as max flow or min cost flow, which allows you to solve matching, tracking, transport problems. All right, so broadly, these are problems and paradigms. And if you open any book on combinatorial optimization, any good book, you will find these. You will find all of them as special cases of a harder and bigger class of optimization problems, the integer programming problems, or even mixed integer programming problems. And it turns out that these simple problems listed here, that they have some funny combinatorial structure that makes it possible to solve them to global optimality in very limited time, whereas this general class of integer programming, these are NP-hard problems that with computational effort can grow exponentially with the size of the input. Good. Now, many of these problems and paradigms, they have an intellectual Überbau, or can be seen from a different point of view, namely in terms of generalized convolutions or generalized matrix product or generalized shortest path problems. And this general view is that of algebraic graph theory, which studies the semi-rings shown here below and a few others. And from the viewpoint of algebraic graph theory, for example, most of what is shown here boils down to just a single problem and even a single algorithm, just in terms of these different semi-rings. So to me, that is I think unifying principles are very important in science, and I think every physicist and also every computer scientist enjoys will like formulations that encompass a big number of special cases. And to me, this is one such formulation. And so we will talk about algebraic graph theory also. Good. Now, that was a longish introduction. And next we come to the science, namely really talk about shortest paths and their use in computer vision.